Welcome back. So we were discussing the consequences of the great orthogonality theorem. So as a consequence, we said that there are certain rules. So what did we find in the last class? That the rule 1 is the sum of the dimensions square of any given representation, ith representation, is equals to the order of the group. From there, we also found that sum over characters corresponding to identity operation is equals to H. And as rule 2, we found that sum over all the symmetry operations, if we take the characters of characters corresponding to any particular given representation and then sum it over all the symmetry operations and square it and sum it over all the operations, then that is equals to the order of the group. And as a third rule, we found that any two irreducible representation will be orthogonal to each other. Okay, so meaning that if I choose ith representation and jth representation, then they will be orthogonal if I not equals to j. Okay. And as a fourth rule, we said that the characters, so characters of irreducible representations of the symmetry operations belonging to a particular class are identical. And as a proof, we said that basically we have proved this one because the elements of a class are conjugate to each other, and the matrices that represent those elements, in our case symmetry operations that forms a class, will also be conjugate to each other, and we have proven that conjugate matrices have identical characters. So this is already proven. Now the fifth rule, which is another very important one, says that the number of irreducible representation for any point group, say for a given point group, is equal to the number of classes that is present in the point group. So this is really important one, and we can quickly cross check that one. So if you again go back and look at the character table of ammonia, what you will see that there are three classes: E, the class of C3, and class of sigma V, and the number of irreducible representation is also 3. So you can pick up the character table of any point group and you can verify this one. Okay, so we are also not going to give you the proof because it's pretty lengthy. However, if you consult a book, say for example by F.A. Cotton, then you will see that they do not give a direct proof, but at least they will tell you that the this relation, that is number of IR is equal to the number of class, it can be proven in an indirect way, that is that a number of irreducible representation has a upper bound which is given by the number of class. Okay. So, let us try to illustrate all these 5 rules, okay, that we have got from great orthogonality theorem, and this will help us a lot, because in this process while doing this illustration, we will be able to see how one can form a character table for a particular point group. Okay, so let us try to do that. So, let us take a particular point group. So, let us take a point group C2V. We are all familiar with C2V point group. What are the symmetry element that it has? It has identity, it has C2, it has sigma V, and it has sigma B prime. Okay. So, what we will do, we will try to form the character table. Okay. So, to start with, I do not know how it is going to be. Okay. And what we will do exactly is as follows. We will start from rule 1 and we will go all the way to rule 5. Okay. And then ultimately we will form the character table. And remember, this character table that we are going to form, that is going to give you the characters of irreducible representations. We have learnt earlier that we can form any representation that may be reducible or may not be reducible. But what we are going to do now is that we are going to form the irreducible representation which are possible for this particular point group, and thereby forming the overall character table. So, what is our first rule? First rule says that sum over L square is equal to the order of group. Fine. So, here I have 4 symmetry operations, and all of them form a class by themselves, that we have seen quite some time back. Okay. So, the order of the group is the number of total symmetry operations. So, order of group is 4. So, now as per the rule 1, what I have, that sum over Li square equals to H. So, I have L1 square plus, okay. So, now before even going here, I can take the help of this particular rule, okay. That will really help me. How? I will know what is the number of irreducible representation that is possible. Okay. So, now here I have 4 different classes. So, number of class is equals to also 4. So, therefore, I can have 4 different irreducible representations. So, let us just give them the name gamma 1, gamma 2, gamma 3, gamma 4. In one of the previous classes I mentioned that in general we try to use this term gamma to for any given representation. Okay. So, later on we will try to figure out what this gamma 1 and gamma 2, gamma 3, gamma 4 actually stands in terms of the Mulliken term symbol. Okay. Excuse me. Now, I know that there are 4 irreducible representations because there are 4 classes. So, now come back to rule 1, which says that sum over Li square equals to H. So, sum over Li square equals to 4 in our case. Precisely what I can say, that L1 square plus L2 square plus L3 square and L4 square equals to 4. Alright. Now, since I will have 4 irreducible representations, none of these representations can have dimension 0. The minimum dimension that is possible is 1. Okay. So if I keep that in mind, then only one way I can solve this, that is all of this L1, L2, L3 and L4 are 1. Therefore, it means that their dimensions are all unity. Okay. So, dimension of any representation can be found from the characters of that representation, and the character correspond to the identity operations. So, therefore, what I can write is this is 1, this is 1, this is 1, this is also 1, right. So, we got 4 numbers here, okay, corresponding to 4 irreducible representation, and all of them are one dimensional representation. Now, one dimensional representation means only one number in the matrix, fine. So, you can easily figure out that there is no possibility of having any other number other than 1. Okay. So, either that will be plus 1 or minus 1. Now, the first irreducible representation we can try to find out in a way. If I go to rule 2, which says chi of r, r, and if I take the square is equals to, in our case, 4, and suppose this I is my gamma 1. Okay. Therefore, what I have then chi of E plus square plus chi of C2 square plus chi of sigma V square of plus chi of sigma V prime square is equals to 4. Now, again already I said that all these characters can be plus or minus 1, okay, by its definition, because it is a one dimensional matrix representation, right, essentially. So, therefore, I can have all these characters as 1, even plus 1. So, if I do that, I get this. You can verify this one, 1 square plus 1 square plus 1 square plus 1 square is equals to 4. So, this rule 2 is verified for this particular representation. So, I got my first irreducible representation here. Now, let us take the help of rule 3, which says that any two irreducible representation are orthogonal to each other, meaning that if I have another irreducible representation here, suppose if I write like x, y, z, some arbitrary numbers, okay, and I know of course that this x, y, z can be either plus 1 or minus 1, nothing else. Now, in that case, this and this if I multiply, I should get 0, because they are orthogonal, mutually orthogonal, and that is true for any two IRs belonging to this particular group. Okay. So, that is possible if two of them are minus 1, right, because here all are positive plus 1. So, if I have 2 plus 1 here out of these 4 characters in a representation say gamma 2, then 2 of the characters, if it is plus 1 and other 2 are minus 1, then if I multiply with this one 1 to 1, I will get 0. So, the orthogonality will hold, correct, fine. So, without worrying about anything else, I can just arbitrarily first put, I put minus 1 here, minus 1 here, plus 1 here, and then say 1 into 1, 1 minus 1, 1 minus 1 and 1 1. So, I get orthogonality verified. So, now I have to find out the other two. So, what I have to do, whatever the irreducible representation that I will form here in terms of plus or minus 1, that should be an unique one, that should not repeat one of the IRs, and at the same time that should be orthogonal to any other IRs. So, I can do that quite carefully. So, now I make it plus 1, and this one if I make it again plus 1, and so okay, so I have made this one minus 1, right. Therefore, I can make this one as minus 1 and this one as minus 1. Now we can verify whether this orthogonality holds. So here minus 1 1 will give me minus 1, and here minus 1 into plus 1 will give me minus 1, and this combination and this combination will give me plus 1. So overall this multiplication will be 0. Again, if I check with this gamma 1, then obviously I can see that there are 2 plus 1s and 2 minus 1s. Combining with this IR having all plus 1s will give me 0. So I am left with the last one that I can fill up in this way, that I can make this one as minus 1 and this one as minus 1 and this one as plus 1. Okay. So you can easily verify that this is also orthogonal to any one of them. Okay. So you see how easily we could form this character table. Okay. Now we are just left with assigning this Mulliken symbol, which also let us do it right away. Now what we know that all the one dimensional irreducible representations are given terms as A or B. So I do not have any scope of having E or T. So this will be either A or B. How I decide about whether it will be A or B? We look at the symmetry of the character correspond to the principal axis of rotation, that is here it is C2. So this one is positive, so therefore this guy is definitely, it belongs to A type. Similarly this one also is symmetric with respect to C2, so this also will be A type, and gamma 2 and gamma 4, they are anti-symmetric with respect to C2. Therefore, this guy will be of B type and this guy will also be of B type. Gamma 2 and gamma 4 will be B type. Now, we have to differentiate between two A's and two B's, right? So, that can be done by putting some subscript, okay, 1 and 2. How do we put the subscript? We look at the perpendicular C2s, or in case perpendicular C2s are not present, we look at the sigma V's. Okay. So if I look at this sigma V, then this is or maybe we can for A, this sigma V is symmetric. Okay, the character with respect to sigma V is symmetric. So I put it as 1, and then the another A, if I look at, this is anti-symmetric with respect to sigma V. So let's put 2, and now this B is symmetric, its character is symmetric with respect to sigma B. So I give this one as B1. Then I am left with this one, it will be B2. Let's verify this one. Yes, it is anti-symmetric with respect to sigma V. So I got my main character table. Okay. So this is what we need. Now about area 2 and area 3, that also one can easily verify. So all you have to do, you have to take the these functions, say x, y and z, or rx, ry, rz, or on the other side xy, xz, x squared, all this individually, operate all the symmetry operations belonging to C to V, and you generate the representations. If you form representations which are irreducible, you can immediately find out that which irreducible representation that is. Okay. Suppose you are choosing z as your basis function, so your basis set comprises only z. Then if you form a representation, so you will find that this is the irreducible representation that it belongs to. So therefore you will be able to say that if you go to area 3, then you can write z against A1. Similarly, y or x or rx, ry, or the other binary combinations of this Cartesian coordinates, you can fill up the area 3 and area 4. Okay, and that kind of exercises we will be we will need to do when we will particularly do the normal mode analysis. Okay, that will be coming probably in the 7th week of this lecture series. Okay, so this is a very nice illustration for illustration of all those rules that we talked about and we obtained from great orthogonality theorem, that using those 5 rules we can very easily form the character table of any particular point group. So we took C2V as an example and we proved it. So what we will do, we will try to illustrate this with the help of another example, which is a little bit more complicated than this simple point group. So what we will do, we will choose C3V instead of C2V now. Alright. So you have already seen the character table of C3V. Now we will see how do we form that character table. So how many symmetry operations C3V has? It has total 6 symmetry operations, 2 C3 and 3 sigma V's and of course identity is there. Now when you write the character table, you write in terms of the class, because any symmetry operations belonging to a class will give you identical character. So there is no point in writing it very much explicitly. So what is meant here is that I have C3 and C3 square, 2 operations. Both of them will have same character corresponding to any particular irreducible representation. So C3 and C3 square belong to a class. Therefore what we write instead is 2C3, so that I know that there are 2 operations, but both of them will have the same character, and same is the fate for the sigma V's. Okay, 3 sigma V from the class. So I write in this way, and with this we can we will start forming the representation. Okay, so we will stop here today, and we'll come back tomorrow with when we will form the character table of C3V point group. Thank you very much for your attention.